Okay, this is a good problem because it gives us now an opportunity to look at two decision variables, and so we have to figure out how to model given uh, given this situation. So we have this beer company, and in case you didn't know where Wayne Winston was originally teaching, it was at Indiana University in Bloomington. So that's why there's all these references to Bloomington. Into two territories. If the company spends X $1 on promotion in territory one, it can sell 60 X1 to the 1/2 cases of beer there. And if it spends X $2 in territory two, it can sell 40 X2 to the 1/2 cases of beer there. So what does this mean? Well, it means that the actual sales is proportional to the amount of money spent advertising. And the constant of proportionality is 60 in one and 40 in the other, but that the amount of money you spend, that relationship is what? Square root. Okay. So you got to quadruple the money you spend to double the effect. Right? You get that? You see how that works? Okay. So let's go ahead and uh, plug the values in here. All right. So this first table that I'm going to fill out, and this is what you need to be thinking of when you're doing this. This first table that I'm going to fill out, I've got my constant A and my value Y, where A is the constant of proportionality and Y is the exponent. So for territory one, A is what? 60. And for territory two, it's what? 40. And Y in both cases is what? 1/2, right? I guess that took that as a number, right? Okay. My selling price in territory one is $10 and incurs $5 in shipping and production. Oops. In territory two, it sells for $9 and incurs $4 for shipping and production costs. And my budget for promotion is $5,000. Okay. All right. So far, this kind of looks like all the linear problems that we've done before, doesn't it? Kind of like those blending problems that we did once before. So what do you think my decision variables are? Sure, the amount that I'm going to spend on promotion. So I'll go ahead and highlight those. Now, let's just plug in some numbers just for starters. Okay. How much demand will I generate for that amount spent? Well, it's going to be different in the different territories, right? So in territory one, the demand is going to be A times amount spent on promotion raised to the 1/2. Can I copy that formula over? I think I can. I copy it over, it should go to C's, right? Yeah, so we're okay there. All right, total amount spent, I haven't calculated that yet, so let me calculate that. All right, so the total promotion cost is equal to that. Shipping and production cost should be a sum product, thank you. It's going to be a sum product of demand times shipping and production cost. And revenue is going to be what? It's also going to be a sum product, again, of demand, and this time unit selling prices. So my profit is going to be equal to my revenue minus the sum of promotion costs and shipping and production. And that is going to be what? Should be my objective function. Okay? So, and again, for those of you that are uncomfortable with the fractional values for demand, let's assume these are in thousands of cases or hundreds of cases. Maybe that makes better sense. Let's assume they're in hundreds of cases. So that's what we're doing. All right, so now let's put together a solver model. Our solver model says I want to maximize profit. And I want to do it by changing the variable cells. Well, the variable cells are the amount that I spend on promotion. The constraints are that the total spent on promotion has to be less than or equal to the budgetary amount. Do I have any other constraints? Other than the non-negativity constraint? Well, you mean on these decision variables. They're non-negative, so that's one bound. Do I want to put another bound on them? If I do, that bound on the individual ones, neither one can be more than 5,000 because that's my budget. But I've already got my total spent bounded by the 5,000. So in reality, those two decision variables are bounded because the sum has to be less than 5,000. So the answer is I don't think there's anything else I can constrain. I think I'm there. So let's take a look and see what I've set up with. I wish I would quit doing that. All right, I'm not going to use multi-start this time. I'm just going to see what I get. So here goes. Solver found a solution. All constraints and optimality conditions are satisfied. Now wait a minute. Why did it not say in all probability it converged on a global solution? Shouldn't it have said that? Okay. So I spent my $5,000 budget. I created the demand that you see, and I generated this profit. Do we believe that that is the correct amount of profit? Why don't we go back just to find out and use the multi-start option, but I'm not going to put bounds on the decision variables. And now see what happens. Okay, so now we get the message because we use multi-start, solver converged in probability to a global solution. And it looks like it's the same values. So with multi-start, we got the same answer as without multi-start. Now, the thing that's the trick with this problem is, yes, first of all, demand is a nonlinear function in both cases. It's nonlinear in territory 1 and it's nonlinear in territory 2. But more importantly, we are also constrained by how much what values the decision variables can take on. They cannot go above that $5,000 budget. So we've really got a more complicated problem than we've had before. Before, we were just trying to find a maximum of basically an inverted parabola. Now we're trying to find a maximum where we've got, if you will, two curves intersecting. Okay? So this is a little bit more complicated mathematically, but as you can see, Solver found the answer pretty easily. Make sense? What questions do you have? Well, you're only going to get the probability dialog if you use the multi-start option. Okay? If you don't use the multi-start option, let me go back and show you what happens when you don't use the multi-start option. Okay? So I'm going to uncheck multi-start. And now I'm going to solve it using the GRG nonlinear. And it says, solver found a solution, all constraints are satisfied. So that's the same dialog you got before. But then look down here what it says. When the GRG engine is used, solver has found at least a local optimal solution. So all that this dialog box is telling you is, for certain, it found a local optimum. And that's all solver's guaranteeing you. So when you get this dialog using for a nonlinear problem, it begs the question, would I get a different answer if I started from a different point? Okay, remember, what point did I start from on this problem? I started from the point of 1,000 here and 1,000 there, okay? That was my starting point. If I started from 0 and 0, that would be a different starting point, all right? And so the question is, since I know where I start has an effect on the answer I get in a nonlinear problem, do I want to trust that dialog that says, based on the starting point you chose, this is the answer I got? Okay? Again, these problems are simple enough that I'm okay with that. But because I did not, in probability, find a global, I would much rather go back and use the multi-start just to be sure. And when I do that, I get the probability of a good solution. Yes. Well, let me show you, and you'll see. Hang on a second. So, uh, so here's nonlinear, require bounds on variables, but now I've only got an upper bound on the variable. So when I say solve, it says I must have both upper and lower bounds. Well, it should, but well, okay. So what it's really telling me is I need to be explicit about the bounds on each variable. All right. So if I'm going to use the non-negative lower bound as one constraint, then for each variable, I should go back and probably do this. I should probably add one that says this one has to be less than the budget amount, and this one has to be less than the budget amount. Okay, so now I've said the total has to be less than the budget amount, and the individual ones each have to be less than the budget amount. And since I've got unconstrained variables non-negativity check, that should, if I'm right, that should allow the multi-start to run with the boundaries set. So let's see if that does work. And it did. Okay. So it's basically telling me it accepts the non-negativity as a lower bound, but it explicitly wants upper bounds on each of the decision variables. Really? Okay. I'm more comfortable. Well, I better be careful how I say this. You can over-specify a model. You can give it so many constraints that it's infeasible to solve. On the other hand, with these kinds of problems, if I can point to where I've set an upper and lower bound on each of the decision variables, then I feel I won't run into issues with the multi-start option. Okay. All right, let's continue with part B. If an extra dollar could be spent on promotion, by approximately how much would the company's profit increase? By how much would its revenue increase? How would we answer this? If we spent an extra dollar on promotion, how much would the profit change? How much would the revenue change? I would use solver table, yes. You could theoretically just plug a number into the equations, but why bother if you've got solver table, right? So let's go in to solver table. And I'll just do a one-way table because that's all I need to do. And so my input cell is budget. I'm going to call it budget. And I want to say the minimum is 5,000, which is my starting point. The maximum is, well, it says by $1, right? So I'm going to give it a maximum value of 5,010 with an increment of 1. So I'm going to use 10 different increases. And for my output cells, what do I want? Well, it says how much would profit increase and how much would revenue increase. So I want profit and I want revenue as my output values. And so now I'm going to hit OK. And there's my answer. So I increased my budget, my promotional budget by $1 here. My profit increased by $2, and my revenue increased by $5, right? Here I increased it by another dollar. My profit only increased by $1. In fact, what I'm guessing here, looking at these, it's actually $1.50, isn't it? What do you think? Do you think those numbers are $1.50? Let's take a real quick look. No, it's even more different than that. Is that what you got? So we get this, all right, is equal to this minus this. So is it $1.55 throughout the range? It looks, yeah, I mean, clearly it's not exactly $1.55 because there's one value that's $1.54 here, but it's almost $1.55. And the other values are 494, 493. All right, so what does this tell you? Is it worth spending another dollar on promotion? Yeah, right? Because I mean, your return is $1.55. Spend a buck, you get $1.55. If you invested $100 in your 401k and you got 150 back at the end of the year, you'd consider that pretty good, wouldn't you? I would consider that very good, actually. So the question really you should be asking is, when does that, can I use the term shadow price? Because that's really what we're doing here, right? That's the shadow price of $1 of promotion. When does that shadow price change? When does it go to something other than $1.55? We don't know that from this example, but I could probably run solver table again, this time maybe going from 5,000 to 5,500 or something like that to see. But here's the thing. Go back and look at the demand functions. Is there a boundary on those demand functions? There's not, is there? I mean, yes, it's a exponentially decreasing value. So at some point, $1 of extra promotion is only going to generate $1 in profit. But that's, I don't know where that is. That's probably way out on the tail somewhere. Wherever that slope gets really, really narrow. All right. The other problem says use solver table to see how a change in the price of beer one affects the optimal solution, and do the same for a change in the price of beer two. You guys want to do that? You want to see what happens? How would you do that? Yeah, exactly. Alex has got it right. Okay, so what he said was you could do a two-way solver table. Now, a two-way solver table is harder to interpret than a one-way solver table. All right. Well, let me show you how that would work. All right. So let's do a two-way table. And what you basically get is parallel dialogues. So the input cell for one would be the selling price of beer number one. So price of, well, it's territory one. And let's use 10 as the minimum, go up to 20 in increments of one. And for input cell two, let's use the price in territory two. And here, let's go from 9 to 19 in increments of one. And again, for the output cells, let's just choose profit just to make it easy to interpret for now. Okay? Is that what it says, by the way? Well, it says affects the optimal solution. So let's go back and also I'm going to choose the amount spent on promotion. Whoops. Okay. So what I did there was I chose B16 and C16, which is the amount spent on promotion, and then I also chose B24, which is the profit. So I'm going to run the solver table now. You can see it's running pretty quickly down there below. You can tell this is a nonlinear problem. There we go. Okay. So now this is what you get. All right. So when the price of beer number 1 is 10 and the price of beer number 2 is 9, you spend 34.62 in territory 1 on promotion. Okay? That's what the solver table is telling you. As you hold the price of beer 2 constant and increase the price of beer 1, you can see you spend more promotionally in territory 1, which makes sense. If I hold the price of beer in territory 1 constant and spend more in territory 2, I'm sorry, I did that wrong. This is the one I should be looking at. If I hold the price of beer in territory 1 constant and increase the price in territory 2, you can see I spend more promoting in territory 2. All right? You have to pay attention to what's the constant value and what's the changing value. Okay? And then here is the profit that is generated. All right, there's the original value, the 20,495. And then, as you can see, as we hold one value constant and increase the other, of course, profit increases. So this table, the profit table, is increasing in both directions because one of the prices is increasing in each direction. Now, you see what I mean when I say the two-way solver tables are a little trickier to interpret. You might find it easier to run two separate one-way tables. One where you hold the price of one constant and allow the other to vary, and then go back and reverse that. But you'll get the same answers that you get here. It's just whichever way is easiest for you to interpret. Okay. Yes? Error values? Really? So you're saying you got an error value where? Starting here on the top row. So you're saying all these values gave you errors? So why didn't I get error values? No, No, I mean, I have the same, go back and look at my solver model. Well, I did constrain each of the individual values to less than 5,000. So maybe that's what maybe that's why. Yeah, yeah. I'll bet that's what it is. If I took off these two constraints here, I'd probably get the same result that you got. That would make sense. No, they're getting errors because they can't spend any money promotionally because they've spent over 5,000 in one territory, right? That's what you're, because it violates a constraint. Yeah. That's good that that happened though, because that brings up a good point, and that is that what happens when solver table does give you an error or an NA or something like that? You have to dig deeper to see what the cause is and to understand why it happened. What it's essentially telling you in that case is that the values that you selected for the decision variables, or not for the decision variables, for the constants, create an infeasibility with the decision variable. And because of that infeasibility, it's giving you an error condition. Now I got around that by bounding them to 5,000. Okay. Well, what do you think about nonlinear optimization so far? Like it, hate it, worried about the next assessment? All right, well, we're going to continue next time. I'll go ahead and stop this now.